The purpose of this experiment is to study the motion of objects moving in 2 dimensions with the constant acceleration, for which projectile motion provides an excellent example. Students will practice how equations of motion are applied in this case and how the different variables of motion are related. For example, students will predict the horizontal range of projectile shot from various heights and angles, and will study the time of flight for projectile shot horizontally different muzzle velocity. Equipment, projectile motion equipment, mini launcher, smart timer, time of flight, 2 photogate heads, photogate bracket, universal table clamp, metric, measuring tape, carbon paper, and a sandbox. Part 2, motion of object projectile at an angle. Part 2, general launch angle setup. Clamp the launcher to the edge of the table using universal table clamp so that the pole launches from and lands at the same elevation. Adjust the angle of the launcher to 25 degrees. Note, with the photo bracket and photogate attached to the launcher, the lowest angle is approximately 23 degrees. Plug the photogate closest to the launcher into part 1 on the smart timer. Plug the other photogate into part 2 in port 2. Turn off the smart timer using the red select measurement button. Choose the time measurement. Using the blue select model button, choose 2 gates model. This will measure the time it takes the projectile to travel between 2 photogates. Part 2, general launch angle. Clamp the launcher to the edge of the table using universal table clamp so that the pole launches from the lands at the same elevation. Adjust the angle of the launcher to 25 degrees. Using the push rod, push the pole into the launcher until 2 clicks are heard. Tape sheet of blank paper at this location. Place carbon paper over the blank paper. Load the launcher. Press the start button on the smart timer. Launch the pole. Use the tape measure to measure the horizontal range are measured. Record experimental data. Enter the value of the angle in degrees theta, the time between photogates, T-gates, and the horizontal range in meters are measured into the table. Repeat the setup for 35, 45, 55, 65, 75, 85 degrees. Using the distance between the photogates and the time between the photogates. Calculate the initial velocity of the ball. Record this value into table. Using the initial velocity and the angle, calculate the horizontal range in meters. Enter this value for each angle into table T. Check the introduction and theory section. Plot both the measured horizontal range R measured various angle theta and the calculated horizontal R range are calculated various angle theta on the same graph. Connect the points R various theta with the smooth line. This is a frame of velocity component. This is the degree. Now initial position x equals 0, y equal 0. Initial velocity v naught equal v naught theta. Velocity component x direction vx equal vi cosine theta, and y direction fy f naught sine theta. Motion is accelerated. Acceleration is constant and downward. A equal G equal minus 9.81 meter square. The horizontal x component of velocity is constant. The horizontal and vertical motion are independent of each other, but they have common time. Analysis of motion. Assumptions. X direction horizontal uniform motion, Y direction vertical accelerated motion, no air resistance. Questions. What is the total time of the motion? What is the horizontal range? What is the maximum height? What is the final velocity? Equation of motion. This is a table equation of motion, acceleration, velocity, displacement. Total time, delta t, y equal v naught t sine theta plus half gt squared. And final height equals 0 after time interval delta t. 0 equal v naught delta t sine theta plus half g delta t squared. Solve for delta t. 0 equal v naught sine theta plus half g delta t. That means delta t equal 2 v naught sine theta over minus g. Horizontal range delta x. X equal v naught t cosine theta. And final y equal 0 time is the total time delta t. Delta x equal v initial delta t cosine theta, and delta t equal 2v initial sine theta over minus g. Then r equal delta x equal 2v initial square sine theta cosine theta over minus g. And that means delta x equal v initial square sine 2 theta over minus g. Horizontal range delta x equal v initial square sine 2 theta over minus g, and conclusion of this horizontal range is greatest for the true angle of 45 degrees. Data and calculation. This is the part 2 general launch angle table. Projectile motion summary. Projectile motion is the motion with the constant horizontal velocity combined with the constant vertical acceleration, and the projectile moves along a parabola.